We're going to talk about surface integrals. There was a section in chapter 14, I believe it was 14.5, where we talked about um, the surface area. I don't know if you recall that, the surface area. So here we talk about the surface integral. The only difference is some function f that's assigned. So in section 14.5, we discussed the surface area, which was some double integral over the region of, it looked like the arc length. It was the square root of 1 plus f sub x, the partial squared, plus f sub y squared, and then dA. So if we take this double integral and assign a function to it, then we call that integral here the surface integral. So note if we assign a function to the surface area, then we call the double integral the surface integral. Now, I need to be honest that there's a little bit more work involved in just assigning a function. We have to consider the so-called surface, or whether it's a surface or a solid, and we have to consider its mechanics. That's most necessary to connect the so-called area with the so-called surface, and then to try to integrate. We do it, and I'll show you my trick. So here are the surface integrals. Basically, what I just got through trying to describe to you is, see, this function f is assigned to the particular surface area. Here they say a scalar function f assigns a number, this function, whatever it is. When you evaluate it, you get a number to each point on the surface. The points on the surface by themselves, we can calculate the surface area. When I assign a function to it, we just call that the surface integral. The whole goal of this, in the long scheme of things, is to try to measure fluid that's flowing over this surface. And the way we'll calculate the fluid is to use this surface integral. That's the goal. But to take that surface integral and somehow examine it by the volume of the fluid. So I can do that by taking this double integral times a function, and we can calculate volume. So that fluid, as it flows, it gives us the flux. And so that's our goal here in this section. What Gauss and Stokes will do for the so-called divergence theorem and Stokes theorem. Stokes is looking at the curl, the rotation of the fluid, and Gauss, or the so-called divergence theorem, is looking basically how the fluid how it diverges from a particular point. So all, even green, they're all really examining the same thing. And you get back to the line integral, and that becomes the summa cum laude of all of this. But they describe it in different ways. So let's see. Look at this surface integral, how it's defined. Again, all it is, it's a double integral. There's a function assigned. You see this radical? That's really that surface area that we talked about back in 14.5. Remember, it was that arc length. So basically, that's all that is. We look at z equal to g of xy. And so, before in chapter 14, we talked about z equal to little f of xy. It's just a matter of naming functions. The reason why he calls this g is that you got a function f over here. That's all. So if it wasn't for this function f, then we'll be calling this little f of xy. Yes, sir?
Where partials come from that function that we assigned?
The partials come from this function g. Yes, sir. Yeah. Little g of xy acts like little f of xy back in 14.5. It's the same thing. My professor always said to us that letters are dummies and not humans. So since letters are dummies, you can change them and they don't fuss, right? But I dare you change a person and say, look, you can't have this anymore. I'm going to give it to this guy right here. You got a big fight on your hands, right? Now, when the letters start fighting, you better check into an insane asylum, right? So my P was upset with my H. Okay, so yeah, that's right, yeah. So I'm going to show you that this radical shows up all the way through this section, and I have a neat way of getting it, and the way I write it is this. Let capital G, call it g of x, y, z, if you want to be formal, equal to z minus little g x, y. I will refer to this as just capital G. Take the gradient of capital G. So when I do that, I get negative g sub x of xyi minus little g sub y of xyj plus k. Now take its norm or its magnitude and we get the square root of, if I start with the k, that's just 1, right, plus g sub x xy to be squared plus g sub y xy all to be squared. You see, this is the same as that radical right there. So I will refer to this particular theorem in terms of this surface area. Hadn't reduced it yet to, oh boy, there goes streaks again. Starting off too early. See if we can put the pieces back together again. I want to write R, but there's a reason for that. This double integral over the surface reduces the double integral over the region. So here, basically, we're going from the third space dimension to the second space over S of f of x, y, z, ds. This is this double integral over the region. Watch this. If you go into the region, that means that I got to get rid of z. I got to write z in terms of x and y. That's all that means. So that's why this becomes f of x, y, z is g of x, y. And then here times the gradient of the norm of g, dA. So I write it like that. Well, first problem. So here, evaluate the surface integral. So notice that to evaluate the surface integral with respect to the surface, we have to reduce this guy to the region. That means that f of x, y, z needs to be written as f of x, y, g of x, y. So this is x squared plus y squared plus x plus y to be squared, because z is equal to x plus y. Now, since here we're bounded by these functions, this is bounded by a cylinder, this implies that the region, remember we're going to R again, the region is, the radius goes from 0 to 1, and then theta, it's the complete circle, goes from 0 to 2 pi. I noticed on the test that I gave back that those who had issues with certain problems from that test, I saw that you had trouble when you were converting. Some were trying to make a line integral a double integral. We hadn't gotten to that yet. We'll deal with that stuff, with these sections coming up here. So if it's a line integral, it's just a single integral. And then some, I noticed you tried to put a double integral, and then you tried to do the polar conversion like r, dr, d theta. It's just a single integral for that line integral. And you're just integrating with respect to t. So just want to be careful with that. So if we convert here to polar coordinates or cylindrical coordinates, however you want to call it, that means that the function f needs to also be converted, in that manner as well. So we'll do that, but let me deal with my capital G. So capital G is z minus little g of x, y. Well, this is z minus x minus y right there. So I take its gradient based on my instructions. So this is negative I minus j plus k. And then I take its norm. Do you see that's the square root of 3? 1 plus 1 plus 1? Are you with me? Everyone, okay? And you can see how that comes in the answer as well, right? So we got that. So that norm is going, I was on the previous page, I'll write it again. So this double integral over the surface of f of x, y, z, ds is the double integral over the region of f of x, y, little g of x, y times that norm of the gradient of g, we just found that to be the square root of 3, times dA. So the next thing we have to do is to convert this function f of x, y, z to its polar form. So what I'm going to do is just write it out again. This is little f of x, y. This is g of x, y. This is equal to x squared plus y squared. You FOIL that x plus y to be squared out, that's x squared plus y squared plus 2xy. X squared plus y squared plus 2xy. So this is 2x squared plus 2y squared plus 2x times y. So when I convert this now to its polar form, so this is f of r theta g of r theta. This becomes 2r squared plus 2r cosine theta times r sine theta. So now I'm ready to write this surface integral as some double integral. I'm going to evaluate theta first, maybe something to go out. So this is 0 to 2 pi and then 0 to 1. I think it was x squared plus y squared less than or equal to 1, yes. And then we have the function, right? It's the function. So this guy is this 2r squared plus 2r squared cosine theta sine theta. So this is 2r squared plus 2r squared cosine theta sine theta. See here, double integral, we're converting to cylindrical or polar coordinates. I have to have now that r factor, and then this is, I'm using d theta first, dr. Oh yeah, by the way, I am working on that problem that I wanted to give you. I've been typing on it, and but I've had other things come up. I'm helping the Ministerial Association in Athens and Limestone County with some work, and so that's kind of had me bogged down assisting them. So, but I have not forgotten about you, so I think it'll be a really good exercise for you when I give it to you, okay? So let's work this. This is 0 to 1, 0 to 2 pi. Multiply that r through, so that's 2r to the third plus 2r to the third cosine theta sine theta d theta dr. So I'm going to integrate with respect to theta. How do I integrate that? What do I use to integrate with that cosine times the sine? Brother Lewis? I want to integrate. We're integrating everything, but the key is to integrate. How do you integrate cosine times sine? What do you say? Yes, sir. Use substitution. Very good. I couldn't have said it better myself. Bravo, Brother Lewis. Bravo. I'm drinking green tea this morning, directly imported from China itself. And I just want to tell you, I told my secretary when I left from up there, I told her that I loved her, and she was shocked. So look, I love y'all too, okay? This stuff makes you, kind of like, woohoo! So I love everyone. Get that away from you, yeah, man. I don't need the hard stuff, just the green tea, Oh, boy. So, it is, that's right. So this is 0 to 1. I'm going to integrate with respect to theta. Got to be careful. This is 2r to the third times theta, right? Then this is plus. You let u equal to sine, and so du is that cosine d theta. So that becomes u squared over 2, right? So I'm going to put that there, but you're going to see this 2 is going to go away because it's going to be 2 divided by 2. So this is r to the third sine square theta. Evaluate the theta from 0 to 2 pi. This is dr. Now check this out. That sine square theta evaluated from 0 to 2 pi is just 0, right? I'm hitting sine on 2 pi, that's 0. Then I'm hitting sine on 0, that's 0 too. But that leaves that theta in the front, that theta right here. So this guy, I'm just going to write that. You do the evaluation, that guy goes to 0. right? But then don't forget, I'm going to have replace that theta with the 2 pi. So this is the integral from 0 to 1 of 2 r to the third times 2 pi dr. So I have 4 pi in the front. Oh man, I forgot that square root of 3. Forgot this guy right here. Gotta put him in there. What are these streaks coming from? I don't even know. Mercy. So it's like when I get ready to erase, I don't know. I think it's the pen. So this is square root of 3, then that was r d theta dr. I'm going to put that square root of 3 here. So this is 4 pi times the square root of 3 times r to the 4th all over 4. Evaluate the r from 0 to 1. So all we have left is just pi times the square root of 3. Okay. Any questions there? Try your hand at that one. So if you look at the function f, so f of x, y, g of x, y is the square root of x squared plus y squared plus the square root of x squared plus y squared to be squared. This is the square root of basically 2x squared plus 2y squared. 2x squared plus 2y squared. Isn't that r times the square root of 2? Okay. Now, z is equal to, in terms of polar coordinates, why am I going to polar coordinates? Because I'm giving us a circular disk right there, right? So here, z is equal to r, right? Because r is x squared plus y squared. That's the square root of x squared plus y squared. This is the square root of r squared. So z is just equal to r. This implies that capital G is equal to z minus r. This implies that the norm of capital G is negative 1 times I for the r position, for the theta position, for j is 0 plus k. This implies that the gradient, the norm of the gradient of g is equal to the square root of 2. Are you with me so far? Okay. So now, the region is defined from 0 less than equal to r less than equal to 2, 0 less than equal to theta less than equal to 2 pi. So this double integral over the region, can go ahead and calculate that now. This is, say, 0 to 2 pi, 0 to 2. The function f, little f, just becomes r times the square root of 2. This is r times the square root of 2. Times that norm of the gradient, that's the square root of 2, times the r factor dr d theta. Square root of 2 times square root of 2 is just 2. This is 2 times the integral from 0 to 2 pi. You see how the polar coordinates helps us in our conversion? Makes all that a whole lot easier. This is r to the second dr d theta. Integrate with respect to r. So this is 2 times the integral from 0 to 2 pi. This is r to the third over 3. Evaluate r from 0 to 2 d theta. So that's 2 to the third. So it's 2 times 2 to the third over 3 times the integral from 0 to 2 pi d theta. So that's 16 over 3 times 2 pi, 32 pi over 3. Okay. What was that again? With that gradient? Yeah. Yeah, that's right. Yeah. All right. Let's move on. Any questions there? Sorry. Okay. Basically, the idea in this section, there are 3 subsections. One is the surface integral, the second is parametric surfaces, and then the third is the flux. So for each subsection, my goal is I work a problem, you work a problem. Well, we're not doing so good. But anyway, so it's 6 problems in all. And so, but I need you to definitely try to get it, guys, because it's better for you when you can get it. It's better for you. Parametric surfaces and surface integrals. What is the possibility that the surface that you're given is based on parameters? there are other factors attributing to the structure of that particular surface. Those parameters can be defined in so many different ways. That's the cool thing about the mathematics, is that we can build the structure to allow whatever parameters that you want to suggest, whether the parameter may be temperature, the parameter could be pressure, doesn't matter what those parameters could be, but we can still build the model here, and we call it the surface integral that depends on certain parameters. So the x, y, and z, they're there, but they're being produced by something behind the scenes. And what they're being produced by are these parameters. Could be time as well, but time is typically the given parameter normally. So there could be other parameters out there. What are they? So many. It's vast. So when we have that, we say, look at this, that R, the position vector, is based on two vectors u and v, but those here become the parameters, because we normally see this. We normally see R of t is equal to x based on ti plus y of t j plus z of t k. Right? Well, that one known given parameter is typically time. But what if there's more than one parameter? Maybe another out there. So we call those two parameters u and v. U and v form their own set and form their own space, where we look at u and v, whatever these parameters are, as being close to each other. Close in the sense of forming vectors. So u may shoot out from a point here, and v may shoot out in that way from that same point. If that be the case, then there's an angle, theta, and these two vectors form, for us, a parallelogram. So then our goal is to resort back to something we talked about in chapter 11, where we talked about two vectors, two adjacent vectors, and from there we can build a parallelogram and then find the area of the parallelogram. When you find the area of this parallelogram, we call this region D. It acts like R. It acts like X and Y, but we have these new parameters, U and V. So in the region R, in the XY coordinate, you're looking for the base area. Here I'm looking for now the base area in D, this new region that depends on U and V. So now to build the so-called area for the parametric surface, we need to incorporate the idea of the area of the parallelogram, because the area of the parallelogram, if you remember from chapter 11, if you don't, I'm going to tell you, is equal to the norm of the cross product. So here, the area of the parallelogram formed by the adjacent vectors u and v is precisely the norm of the cross product of u and v. But here, u and v is just not u and v anymore. U and v comes into play with this so-called position vector r. So take that into consideration too. So note we need the base area of D this area is formed from the norm of the cross product of R sub u, R depends on u, and R sub v. We use the parallelogram, or we use the definition of the area for the parallelogram to give us this area. So here, notice here that the area here for this parallelogram is the norm of the cross product of u and v. So that's what we use. In this section, we're using capital DS. So just for right now, just bump that. Right? This part right here, this is what we just got through doing. Right? This is the surface integral. So that DS right there, again, I told you that DS is an arc length. So it acts like little ds, that square root of 1 plus those partial squared. So ds capital DS becomes in the same format in the previous sections when we dealt with the line integral. I don't know if you recall the line integral we called it the line integral if it was you had f dot dr, that gave you one thing, but then you had another that dealt with the line integral of some function ds, right? Well, that ds was said to be the norm of r prime of t times dt. Well, in like fashion, our ds, capital DS here for the surface integral, is still in that same accord. Now look, check this out. See, I told you that capital DS is the norm of the gradient of G times dA. Right? Just got you doing that norm of that gradient of G. Right? Well, look, this norm acts in the same accord with the parametric space. They act the same. So I need to still calculate some magnitude. So here the magnitude now based on the parametric surface becomes this cross product, the norm of this cross product. So just in a nutshell, if it's the cross product and then you take the norm of that, you get the area. So that's the goal, is to get the area. So this norm of the cross product of R sub u crossed with R sub v is the base area for this new region D. Well, that cross product is precisely this right here. It's the cross product based on the cross product definition. Now let me tell you, if you were back in chapter 11 and you were talking about the cross product, of, let's say, two vectors, u and v. It is u crossed with v is the determinant of I, j, and k. That's always in your first column. Then it becomes the coordinates for u. So u sub 1, u sub 2, u sub 3. Then the coordinates for v, v sub 1, v sub 2, v sub 3. Right? That cross product is the same. You know how we calculated the curl? That's the same fashion. So we set that up, minus j cross product of two vectors. Uh-oh. It's just doing things by itself. So let's go ahead and just find it. This is u sub 2 minus v sub 3i minus u sub 2 times v sub 3 minus u sub 3 times v sub 2 I, then minus, delete the jth row and column, u sub 1 v sub 3 minus u sub 3 times v sub 1 j, then plus, delete the kth row and column, u sub 1 times v sub 2 minus u sub 2 times v sub 1. Okay. The same way how we found the curls, that same structure here. But now, for the cross product of u sub r and u sub v, well, they're based on those partial derivatives. So here, this second row becomes the partial here of u, or to say with x, y, and z, based on u. So I like to say the partial of really u with respect to x, the partial of u with respect to y, and then the partial of u with respect to z. That third row becomes the partials with respect to v, if you will. So we'll need that to get the area for the base. And again, I was showing you earlier where u and v are adjacent vectors. So we're computing the parallelogram. So now let's look at a problem. Evaluate the parametric surface integral here, where this guy becomes this. This is the double integral of f of x, y, ds. This is equal to now this double integral with respect to the new defined region. What is it? D is this guy right here. Okay? And this is f of x with respect to u, and then y with respect, it's u and v, should be, x with respect to and then y with respect to u and v. And then this is times the cross product of r sub u cross with r sub v. And that's the area. So let's go ahead and find that cross product first. So this is r sub u cross with r sub v. The first row is I, j, k. The second row is just the partials of r with respect to u. The partial of r with respect to u. So this is 1, 0, 0. Right? There's only one u there, that's that I. So the partial of r with respect to u there would be just 1 times I, and the other components are 0. This last row is the partials with respect to v. So the partial of the first one with respect to v is 0. The partial here of this y with respect to v is 1. And the partial of the kth position with of sz with respect to v is just 2. If you have a row with 2 zeros, only one term, then you can start there and you can compute that determinant. So here, I'm looking at this row. So what I'm going to do is to say that this is 1, that 1 there, times, I delete its row and column, delete its row and column. So when I do that, let's see here, put that in blue, delete its row and column. Look at the cross product now, 2j minus k. Now I have to note the sign, the permutation signs. This is plus, negative, plus. This is negative, plus, negative. This is plus, negative, plus. What do you mean, what signs? You remember back for the cross product, look, this is plus. See that negative right there? And this is plus, because I'm working along the first row, plus, minus, plus for the permutation signs. Here, if I work along that second row, it becomes negative, plus, minus. And you could find it just on the old-fashioned where you get the same thing. Anyway, this has to be a negative there. There's that negative sign there. So this is negative 2j plus k. But here I need the magnitude of it. I've got to find that norm. So here, the norm of r sub u crossed with r sub v is equal to the square root of that negative 2 squared plus 1 squared. You get the square root of 5. Now I have to define this f with respect to r. So f becomes, it's u plus 5, but look, this is x, and this is y, and this is z. So this is y plus 5, so this is my u and my y. Sometimes in my head I say the same thing, but so this is u plus 5, y, o, u, y. This is y plus 5. So the y here is v, so this is v plus 5. So the function that I'm going to evaluate is v plus 5 there, and then that norm is the square root of 5. So we have the double integral. If we compute the u out here, u goes from 0 to 1, v goes from 0 to 2. And this is the v plus 5 times the square root of 5. And then we're doing dv du. Put the square root of 5 out in front. Let's integrate with respect to v. So this is v squared over 2 plus 5v. Evaluate that from 0 to 2 du. So that gives us the square root of 5 times the integral from 0 to 1. This is 4 divided by 2. That's 2 plus 10 dv. So we get 12 times the square root of 5 times the integral from 0 to 1 dv. This is just 12 square root of 5 times v. V evaluated from 0 to 1. That's just 12 times the square root of 5. Now let me do the next one so that hopefully it'll sink in, and time is about to get us. I want to definitely finish just this section today. We get through 15.6. 15.6 for me is always a long section, so I always try to cover it. If I have one class period, try to cover it within that class frame. Let's work the next one, make the parallel between this next problem and this problem right here. They work the same. I did a lot of explaining, and sometimes it takes a long time to explain. Very easy to work the problem. So I just work the problem here. So now this f becomes, look, this is x, this is y, this is z. So this guy is 3 times y, that's sine u, minus x minus cosine u. Okay. So I have d is there. So now we need to find the cross product. So r sub u cross with r sub v, get I, j, k. I take first the partials of this r function with respect to u. So that's negative sine u. This becomes cosine u, and that's 0. And this is 0. Take now the partials of r with respect to v. That's 0, 0, 1. Permutations for the determinant: plus, negative, plus, negative, plus, negative, plus, negative, plus. So this guy, I'm going to look, I have a row here with 2 zeros and a 1. I'm going to use that guy. I'm going to delete its row and column and multiply the crossing. So this is cosine u I. And it's minus this negative, so that's plus sine uj. Now, if it's just cosine and sine like that, its norm, do you agree with me, it's just 1? Because you take the cosine squared plus the sine squared, you get 1. The square root of 1 is just 1. So we have this double integral. Here, this was 3 sine u minus cosine u. 3 sine u minus cosine u. And if we use, let's say here, du dv, and the u goes from 0 to power over 3, and the v goes from 0 to 1. So integrate with respect to the u. This is the integral from 0 to 1. This is negative 3 cosine u minus sine u. Evaluate the u's from 0 to power over 3 dv. This is the integral from 0 to 1 of negative 3 cosine power over 3 minus sine power over 3. This becomes minus, this minus is plus 3 times cosine of 0 minus this minus is plus sine of 0 dv. Now I need some help because I do not memorize anything. I was working, a student sent a question in Calculus 2 to me in Web Assign, and it was, measure the distance between a point and a line, and, I forgot the formula. I forgot, and so, and I don't like looking in books. It takes too much time. So what do? I just derive it because I know where everything's coming from. So I just built the whole thing right there and just worked it out. You take the point, you're given the line gives you direction numbers, right? Those direction numbers are important for that plane. And then since I'm given a point, and then they give me the line, I get a point from the line that I can build the line segment you call PQ. And so I'm looking for that normal vector, that guy that stands straight up, that becomes the distance. Right? And then, so then I'm able to calculate it. Using the same idea here, I have to use the cross product to get that area, and then take the area divided by the base leg, gives me the upper leg, the height, and I get what I'm looking for. So anyway, I forget all this pi's over 3's and all that kind of stuff, so no problem. This is 1, this is 2, the square root of 3. This is 60 degrees, pi over 3. Right? So cosine of pi over 3 is 1 over 2. Just the integral from 0 to 1, negative 3. This is 1/2 minus sine of pi over 3 is the square root of 3 over 2. Plus 3, cosine 0 is 1, and then sine of 0 is just 0 times dv. So we can pull all that out in the front, and so this is negative 3/2 plus 3 minus the square root of 3 over 2 times that integral from 0 to 1 dv. So here we get, that's 6 minus 3 over 2, so that's just 3 over 2 minus the square root of 3 over 2 times v evaluated from 0 to 1. So this is just 3 over 2 minus the square root of 3 over 2. Okay? Any questions? Now, we consider the, let me scroll down, the orientation of a surface. We say that you want the surface to be orientable. Here, if it's orientable, then I can measure the fluid that's always flowing at whatever rate, but at some type of constant medium or constant structure. If the fluid is flowing on a surface or around the surface, then it keeps that flow as it goes around. There's no double looping or no funny twist where if I'm on the outside, I must always be on the outside of the surface. Can't be I'm on the outside and then somehow all of a sudden I'm on the inside. So here we define orientable surface as any surface that has continuous partial derivatives, and those continuous partial derivatives are always structured in the same manner. We say that it varies continuously. Simply said, a lot of fancy math talk to say that if a surface is orientable, if the partial derivatives, which I get the gradients are always either positive or the gradients are always negative. They always keep their sign. If the gradient is positive, then I'm shooting out, always. If the gradient is negative, I'm always shooting in. So you can't have the gradient is positive, then all of a sudden the gradient becomes negative. And that means that you're flipping from the outer pointing out, and then somehow you're pointing in. And to get the flux, they want to always keep it as the gradient positive or the gradient negative always. Doesn't matter, but has to be consistent. The gradient is, the fluid is flowing this way, but the gradient is sticking up. So the gradient is going to help you measure the height. So you got the fluid flowing. So if this cup, say for example, had a hole here, and so the fluid is flowing this way, but the gradient is measuring up above, right? So the gradient is going to be perpendicular to the flow. So that's what we call an orientable surface. Now, let's see if we can illustrate that. I need to put it in your hands. There you are. Yes, sir. There you are. Yes, sir. Let me give you this one. This is a fat one.
Okay.
Yeah, your hands are big. So.
No, not really.
We can give the little one for the lady. Let me give you a big one too, Ryan. Good. Since you're precise, Benjamin will give you a small one. Yes, sir. I keep this one. If it's two, it doesn't matter. It's one for you. Yes, sir. One for you and one for me. So now, what we're going to do, I want you to take this guy. See how I'm holding my hands? Like one hand is this way, the other hand is kind of, you're going to twist it one time, then you're going to connect it. Twist once. Maybe the paper should have been longer. Should be one twist. Yes, connect it like that. One left hand twists one direction, the right hand twists in the opposite direction, and then connect the pieces. I got tape. No, that's a nice bow, though. You can put that around your neck and you can wear it to church, you know. That's so pretty. Yes, Mobius strip. Yes, sir. There you go. You got it. Got it. Yes, sir. That's it. Perfect. You are an artist.
I
Yeah. No, ma'am. It's like that. I'll do that right there. You can look at it. And I put the tape. You got it, Ryan. There you go. Yes, sir. Good job, Benjamin. Did you get it, Lou? Yes, sir. Good job, man. Need tape. I think. Was that it? That's it.
Okay, cool.
That's it. Yes, sir. Yeah. Could have been the same one before, but Mobius strip. Yep. Mobius. Here's your tape right there. Okay. Just. You can just keep mine if you want. You just use mine. Yeah, just use that one. So now what I want you to do is take your pencil or your pen. Oh, you still working?
I'm still struggling.
See if I can help you, man. Yeah, it's kind of tricky. Yeah, take your pencil or your pen. I want you to start at one point, and I want you to trace around on that same surface till you get to that same point. Okay? Make one complete loop. Not drawing class. Come on, man. I flunked drawing too, so it sure did. I flunked writing and all that stuff too. I just flunked everything. But anyway, how did you make it? Oh, by the grace of God. So. Yeah, when you make a complete loop, you'll be on the other side, right? Yeah. So in other words, this guy right here is not orientable, right? Because see, if you're following that norm all the way around, it's going to loop in. Then once you get back over, you want to end up back over here like this, but actually you end up over there, right? So it flips. So that's not good. Thank you. Yes, ma'am. So basically, this definition wants to exclude guys like that. That's why. If you got fluid flowing within a pipe, you want that fluid to stay in that pipe, right? Right? Always. You have trouble when the fluid is on the outside when it's supposed to be on the inside. So we want to kick out that guy, that Mobius strip. It did. That's right. When you scroll your pencil or pen around, you end up on the other side. So that's what the so-called definition is all about. Now this normal vector is the guy that they're looking at in terms of saying that if n is positive, it stays positive. So here we say if n is positive, then you have the outward thrust. Now what I'm going to do is now try to measure some liquid that's flowing, and I'm going to create some kind of tubing, and I have the normal vector n that's always protruding. If it's n positive, I'm going in the outward direction. So I want to measure now this fluid flow, making sure that the surface is orientable. That's the key. Now, this is the upward direction here for that normal vector. If it's negative, then we call that the downward normal vector. So we're here. There's nothing wrong with negative as long as you stay like that. You can stay, in that direction, and you can measure the flux, or you can turn n up and measure it as long as you're continuous and constant. Yes, sir.
Is that found the maximum fluid flow?
Yes, sir.
Fluid flow is that kind?
Is it the maximum fluid flow?
Because if you have a 4-inch diameter pipe, it can flow, say, 1 cubic foot, 2 cubic foot. But
That's right.
the maximum, no matter how much pressure you put on it, it's still going to only flow, like, say, 35, 40.
Right, right. Let's look at the definition for it and see if we can piece that together. Is that the maximum fluid flow? From what I've studied, it's the constant or the average fluid flow, basically what we're looking at. But is it the maximum? Let's look and see. Good question. So here, to get this so-called fluid flow, we call it the flux, and we can find it by this so-called flux integral. What we're going to do is actually compute or approximate the volume by calculating the height times the base area. So you got this normal vector here. The dot product of the force of the fluid times the normal vector gives us the height of this column. And then delta S, or ds, if you will, capital DS, gives us the change in the base or the surface area. Okay. So here, the so-called velocity field F indicates the direction of the fluid flow. This flux is the average, so it's not the maximum, Joshua. It's the average. Yes, sir. And how do I know it's the average? Because of this change in the volume. It's computing the summation of all that divided by n. Little n here, the partition. Yes, sir. If we find the maximum, then you're actually taking the result and somehow you're trying to compute a magnitude on that, and we're not doing that. Yeah. Oh boy. Yeah. It got me again, I tell you. I want to be like Barney Rubble and go up to the end of the mountain and just scream, you know? I don't know if you saw that episode of the Flintstones. I think they had a baby and trying to be quiet for the baby and that type of thing. And so I think it was the boss's baby, and they told Barney to keep the baby. Barney or Fred. And so I think it was a dog or something that kept on, bringing a needle, pinching him, making him cry, so making him holler so the baby will wake up. And so Barney had to, if he got pinched by this pin, he had to hold his mouth, turn red, run to the end of the mountain and yell out, "Ah!" Well, that's what I feel like doing when I see this streak pop up on the screen. I can't scream in here, but I can go up to the end of that mountain up there. Then come on back and everything is fine. Sir, what you say, man? Amen, amen. Just the definition of the flux integral. What is it? The double integral over the surface. Here, again, this is the height times the base area. So the fluid flow is being approximated by the volume. The cool thing about the volume is that the volume is based on the velocity force field, capital F, of the fluid itself. Right? So let's look at a problem. Here, find the flux of F across the surface, where N is the upward unit normal vector to S. Let me see if I can help you with this, and that is this, that N is equal to the gradient of G divided by the norm of the gradient of G. And ds is the norm of the gradient of G times dA. So this guy is reduced, and this is what I use, is reduced to the region of F dot product. Here I have N, that's the gradient of G divided by the norm of the gradient of G. It's not dot product times, it's just times there. I'm not going to put that so you don't get thrown off. Then times ds, that's the gradient of the norm, that's the norm of the gradient of G, dA. Well, a couple of things cancel out. That magnitude cancels out. So all you're computing is the double integral over the region of F dot with the gradient of G, dA. That becomes the flux integral. That's all we need. So that's what I use. So let's see how that works out. So we're in the first octant. It tells us that I need coordinates, since it's in the region R, I need the coordinates for X and Y. So if I let here Z equal to 0, because we're reduced to R is in terms of X and Y, where Z is equal to 0, I get 0 is equal to 1 minus X minus Y. This implies that Y is equal to 1 minus X. So that means that here 0 is less than or equal to Y. Since I'm in the first octant, my lowest value for Y is 0. The upper value is Y minus X. Now for X, here we take this equation, 0 equal to 1 minus X minus Y, and let Y equal to 0. To get X equal to 1. So 0 less than equal to X less than equal to 1. And you could have flipped that. You could have said here 0 less than equal to X less than equal to 1 minus Y. That would have been fine. Then down here you would have had 0 less than equal to Y less than equal to 1. Doesn't matter. Okay. So the region is 0 less than equal to X less than equal to 1. And then 0 less than equal to Y less than equal to 1 minus X. So here this capital F is equal to 3. Since I'm reduced to the region R, everything has to be in terms of X and Y. So this capital F is 3 times Z, but Z is given to be 1 minus X minus Y. Minus 4J plus Y. Okay. Well, that's what I need. So this flux, this is double integral here from 0 to 1, 0 to 1 minus x. Capital F is 3 minus x minus yi minus 4j plus yk. That's dot product with that gradient of g. Well, I got to find g. It's the gradient of g, and then this is dA. So what's the gradient of g? The gradient of g comes from this equation here. So given z is equal to 1 minus x minus y, this implies that capital G, we said, is z minus little g of x, y. That is z plus x plus y minus 1. I find its gradient. The gradient of g is I plus j plus k. Everybody with me there? So now I go back to that flux. It's integral from 0 to 1, integral from 0 to 1 minus x. This is 3 minus x minus y, I minus 4. Should be 3 minus 3x minus 3y. I didn't run that 3 through, sorry. Yeah, it's 3 times z. Z is all of 1 minus x minus y, right? So this is 3 minus x. 3 minus 3 minus 3x minus 3y. And then plus yk dot product with the gradient of g. We found that to be just I plus j plus k, and then this is times dy dx. See that dot product? This is integral from 0 to 1, integral from 0 to 1 minus x. So this is 3 minus 3x minus 3y minus 4 plus y dy dx. It's integral from 0 to 1, integral from 0 to 1 minus x. This is 3 minus 4, that's negative 1, minus 3x minus 2y dy dx. Now we integrate with respect to y. It's the integral from 0 to 1. This is negative y minus 3x y minus 2 times y squared over 2, and y is evaluated from 0 to 1 minus x dx. Integral from 0 to 1. This is negative parentheses 1 minus x minus 3x times 1 minus x minus 1 minus x to be squared dx. Let's simplify all of that. Integral from 0 to 1. This is negative 1 plus x minus 3x plus 3x squared minus 1 plus 2x minus x squared dx. See, we get the integral from 0 to 1. Negative 1 minus 1 is negative 2. X minus 3x is negative 2x plus 2x there cancels out. So we have left here just plus 2x squared dx. Integrate negative 2x minus 2x to the third over 3. Evaluate the x from 0 to 1. You get negative 2 minus 2/3. This was a plus sign. Flip Wilson said the devil made me do it. I don't know why this is a negative sign there, but this was a plus sign right there. Right? It's supposed to stay a plus sign. So this is -6 minus 2 is -4 all over 3. Well, I got 5 minutes left. I may be able to squeeze this last problem in there. So, any questions there? Now, what I'm doing for this test, I'm mimicking the test. So, this is the first section. Here's the idea. There were 3 problems that I worked. So, from this section of the test, I give you 3 problems in the same manner: surface integral, parametric integral, flux integral. Okay? And then for the next section, I just give you 1 problem based on the divergence theorem, and then 1 problem based on the Stokes theorem. So it'll be 5 problems in all. So it shouldn't. Well, the problems take a while anyway, so I can't give you too many problems. So even for the online class, the test is very short because the problems just take a minute. Well, let's see if I can work it. I'll work up to 10. If I don't finish, you can finish the rest. Okay. So capital F is xi plus yj plus z, but z is 1 minus x squared minus y squared times k. I need the gradient, so let's find capital G. Capital G is z plus x squared plus y squared minus 1. And its gradient is 2xi plus 2yj plus k. Oh, you know when they say that the normal vector is shooting outward? Well, to get it the other direction, you have to negate the gradient. So you have negative 2xi, negative 2yj, and then minus k. And then that'll give you the so-called normal vector shooting inward or downward, and so you'll be measuring the flux from that way. You can do that, but normally we say you want to find the flux integral based on the outward motion force. So let's put that integral together. Do you see that the region, if you can look at that, the region here, I say if you can look at it, I'm making a big assumption, sorry. Let z equal to 0. And this implies, maybe you can see it, x squared plus y squared is equal to 1. So the region here is based on the radius from 0 to 1 and theta from 0 to 2 pi. You see that from there automatically? Okay. So we can just write it. So this is the double integral. We can say here from 0 to 1, 0 to 2 pi. And F is xi plus yj plus parentheses 1 minus x squared minus y squared k as dot product with the gradient. We found that to be 2xi plus 2yj plus k. Here I'm using, I'm going to put that r factor for the polar coordinates, r d theta dr. And then we'll change x and y to that once we get through taking the dot product. Let's do it like that. 0 to 1, 0 to 2 pi. And this is 2x squared plus 2y squared minus 1 minus x squared minus y squared r d theta dr. This is the double integral from 0 to 1, 0 to 2 pi. We just get x squared plus y squared minus 1 r d theta dr. So the x squared plus y squared just becomes r squared. this is r squared minus 1 times r d theta dr, double integral from 0 to 1, integral from 0 to 2 pi. This is r to the third minus r d theta dr. Integrate with respect to theta. There's no theta there, so that just becomes 2 pi times the integral from 0 to 1 of r to the third minus r dr. This is 2 pi, time just hit me, r to the fourth over 4 minus r squared over 2. Evaluate the r's from 0 to 1. This is 2 pi times 1/4 minus a half. So this is pi over 2 minus pi, negative pi over 2. What did I get? Did I get positive pi over 2? Oh boy, I'm totally off. This brings me to this last lesson of the day, class.
Okay,
This is good. This is good.
I believe you.
I took a graduate class in numerical analysis, and the whole idea of the course was the instructor was a lot of programming. The instructor would give us these programming codes, using all this math stuff, but all these codes, but there were errors in the code. And his thing was, okay, to pass this class, you got to find my error and correct it and get it right. So this is supposed to be 3 pi over 2. You find the area. My time is up, okay? I goofed off in there trying to rush. Yes. All right. Did you see it?